Now we will talk about the bag of words framework for text analysis. So many of our approaches actually use this bag of words framework. And the framework essentially is based on the assumption that the context that words find themselves in does not matter. Now, of course, context does matter. We can't understand words without their context. But at the same time, making this assumption can actually be very useful. So there's a statistician, George Box, who has this pretty famous quotation, which you'll find in a variety of contexts, but I think it applies nicely here, which is that all models are wrong, right? So the assumption that words or that the context that words find themselves in doesn't matter is wrong, but some are useful. And the idea here is that knowing the relative frequencies of words used by politicians and users on social media can actually be quite informative. And this is with respect to topics, with respect to ideology, with respect to incivility, or basically any kind of classification task that you want to take with social media data or text analysis generally. And to just give you an example, if you wanted to classify a politician ideologically, somebody on the right might use the word crime very often. We don't know the context that they use the word crime, but they talk about it a lot. They frequently use that word. Somebody on the left, for example, might use the word healthcare. We don't know the context of healthcare, but if they use it often relative to other words, they're probably more likely to be left-wing. So these kind of words frequencies, this bag of words, is actually very useful in practice, even if the assumption is clearly false. So how do we get from natural language or from a document or a tweet or whatnot to a bag of words? What we do is we create what's called a document feature matrix. And a document feature matrix is a very simple idea. And it's just a matrix of the frequency of words or tokens, and I'll explain what a token is in a document. And so you can conceptually think of this as, so a document term matrix is something of an abstract concept, like what is a document? Documents vary, but you can think of it more concretely, at least in our context, as a tweet feature matrix. So for a given tweet, what are the features or what are the words, the tokens that are in it, or a user feature matrix. So like of all of the user's tweets, what are the words that that user uses? Or however you want to aggregate your data. And the basic idea of a document feature matrix is that the rows of the matrix, and I'm going to give an example on the next slide, but the rows of a matrix represent a single document or a single tweet or a single user's tweets, whatever kind of document you are dealing with your text. And then the columns of the matrix simply represent the frequency of each token that is found in each document or in each tweet or in each user's tweets. So to give you an example of this is a matrix. This is not social media data, but it's useful for exposition. This is a document feature matrix of the policy documents of 5 different political parties in the Irish elections. And so you can see that each row, right, the FF, FG, Green, Labour, presumably Lab, SF, refer to a policy document from a specific party. And then the columns right here represent the number of times or the frequency with which a given policy document includes a given token. So if we look at the Green Party row, for example, this row right here, in the Green Party's policy document, the word or the token people was used 15 times. The word budget was used 26 times. The word government was used 19 times. The word public was used 4 times, and so on. And in the actual policy document, right, it contains tons and tons of words. the actual matrix is going to be much, much wider, right? It's going to be very, very wide. So these cells here are just the frequency with which these tokens are in these documents, okay? But you can think of these rows like this is a specific tweet, or this is a specific user. All the tweets from a given user. How many times does that user use the word people or use the word budget? Okay. Very simple idea. The thing is, you have a lot of choices about how to construct this matrix, and they can have consequences for your subsequent analysis, and that's what I'm going to talk about now. So you have 7 different choices. So these 7 choices are from Denny and Sperling, the article you were to read for this week. And the first choice is with respect to punctuation. Right, so we have words here that are very common, right? People, budget, government, public, minister. But in a given sentence, there are these kind of spaces, I mean just regular spaces, and special characters, right? So this $sign, this percentage sign, this ampersand. And the question is whether you should remove them or not. Often these punctuation is removed, but there might be special cases given the context, given whatever context you're examining in your analysis, that you might not want to remove them, or remove some but not others. So that's a choice you can make. The second choice is with respect to numbers. Often numbers are relatively arbitrary, or at least they're informative or uninformative. But on the other hand, there are some specific contexts where they are informative. So, for example, in a given bill or a given law, if you see section 423 that refers to something in the US Code, that is a lot more informative than, say, like a dollar figure in some budget, which is not going to be understood. It's uninformative. So this is a choice you have to make as well. Do you include numbers or do you exclude them before creating your document feature matrix? The third choice is whether you should lowercase all of the words in your document, which is to say, should you treat a word like Trump with a capital T as the same thing as lowercase Trump? So just for example, in one of these columns, you might have Trump, like how often is the word Trump used in each of these policy documents? Should you have 2 columns here, one with lowercase Trump, one with a capital T Trump? Or should we say that they're the same thing and combine them? So lowercase is actually almost universally used, but it is a choice, right? And just to give you the example here, the word Trump with a capital T almost surely refers to the President of the United States. Whereas if you see a Trump with a lowercase t, it probably refers to the verb, to Trump. So this is another choice. The fourth choice is what are called stop words. And stop words are just common function words. And the examples are the, and, it, and she. And I'll show you some examples on the next page as well. Or you could have domain-specific ones. So if you look at the congressional record, you might see the word Congress all the time, which in another context might actually be informative, but in a congressional context probably is not, and you might want to remove that. These are just kind of common, any common function word that is not going to be informative. And this is just an example of the English stop words. There are various lists of English stop words. There's huge overlap between those lists. It's probably not going to make a difference which list you use. And the list is actually longer than this, so I couldn't screenshot the whole thing. But these are words that you can imagine are not actually that informative about anything that is going to be in your analysis. And so people often remove all of these words from the document before, or the tweet, whatever document you are thinking of, before they create the document feature matrix. And then for Danes in the class, this is an example of a Danish stop word list, which you can find at this website right here. Then the fifth step, or fifth choice you have is called stemming. And this is whether you want to reduce words to their root forms. and to essentially treat them as the same thing. So an example is the word party, partying, and parties, right? They all have the same root. It's the same stem, P-A-R-T-I. And your choice is whether to stem. I mean, it's very, very common that people do this, but should we, it's essentially to ask, should we treat the word party as the exact same thing, in effect as partying, as the same thing as parties, right? So should we have these as 3 separate columns, or should it be one single column, P-A-R-T-Y, where the frequency includes any word like party, partying, or parties? Sixth is the question of what are called n-grams. And this is a question of whether to treat multiple words that are side by side as single tokens. And this is one of the big reasons why we refer to tokens and not simply words, right? Punctuation are not words, and so that's one reason to think of them as tokens as well, because not everything is a word. But also that you can think of 2 words or 3 words or 4 words side by side as a single token. So a unigram is just a single word, right? Like national here, that's a unigram. Debt is a unigram. Defense is a unigram. Or trigrams, or bigrams, or bigrams or trigrams. So a bigram is just 2 that are side by side. So to give you an example, the word national, right, means something much different when combined with debt or defense. So national, defense, these 2 words side by side, means something a lot different from national debt. And so if you construct bigrams, you are essentially creating a column in your document term or your document feature matrix that includes every single word that is in your, every single a pair of words, or if it's trigrams, 3 words that are side by side. So you you end up creating a huge document feature matrix. It gets very, very wide because you have to include every single word that is beside another, and trigrams even more so. And this is quite common. And then the last potential pre-processing step is whether to remove infrequently used terms. So this is essentially done entirely arbitrarily, or at least the frequency that determines whether you should remove a word. But if a word is only used once or twice or a few times, or not in very, very few documents, just remove it, right? And so this is done because these words often don't contribute much information. And they also substantially reduce the vocabulary size, right? As I mentioned, especially with bigrams and trigrams, your document feature matrix becomes huge. You have a huge number of columns because you have a single column for every single word, punctuation, or word side by side, or word side by side if it's with trigrams. So removing these infrequent terms can really shrink your document feature matrix down. So this is just a graphic to explain these pre-processing steps. And I think they do 1, 2, 3, 4. They do 4 different steps, right? We talked about 7. In this case, they do 4, but you can think about all 7 quite easily. And so the example here are 2 sentences from Ronald Reagan's 1981 State of the Union address and Richard Nixon's 1973 State of the Union address. And they're just 2 sentences from each. So Ronald Reagan, the text, the natural language that he's using, there's the sentence he's using, is ending inflation means freeing all Americans from the terror of runaway living costs. And for Nixon, the sentence is, this leads only to inflated expectations, to reduced individual effort, and to a disappointment. And so the first step here is tokenization, to creating tokens out of this sentence. So here they're just doing unigrams. Right? If they did bigrams, you'd need a separate token for ending inflation, and another token for inflation means, and another token for means freeing. You can imagine how this explodes your matrix. You get a really huge matrix. This is just unigrams. So they're just taking every single word plus punctuation separated by spaces. And N becomes a token, inflation becomes a token, means becomes a token, freeing becomes a token. All of these plus the punctuation at the end. And they do this to both of these, or to all of the documents in your corpus. A corpus is just a set of text. So they create these tokens through what's called tokenization. And then they do pre-processing steps. So this is n-grams. They chose unigrams. So really there are 5 steps here because they chose unigrams and not bigrams and not trigrams. And the first step they do, or the second step, I guess, after choosing unigrams, is they remove punctuation. So this red, these red cells, that's a period, a comma, a period, they remove those, right? So so all of those are gone from these tokens. You're left with this smaller subset of tokens. And they also remove these stop words, right? So anything in yellow here, all, from, the, of, this, only, to, etc. So you're shrinking your token list down by removing punctuation and stop words. And now they do 2 more pre-processing steps. The first is lowercasing, right? So you can see here that ending has a capital E, it becomes a small e. Americans has a capital A, it becomes a small a. And then they do stemming, right? Stemming is to remove endings to words like ing or ion. So it becomes end in inflate, right, for inflation. But you can see now that Reagan, who used the word inflation, and Nixon, who used the word inflated, they both now have a token that is in common. Inflate, inflate. So now we've lowercased and stemmed. We've gone from this natural language to these tokens, these unigrams, to these removing punctuation and stop words, to this lowercasing everything and taking off the stems. And now we're going to finally create our document feature matrix. So now the documents, right, our documents are the sentence from Reagan. The next column is the sentence from Nixon. And then this matrix would actually be longer than this because there are more tokens than 1, 2, 3, 4, 5. But this is just a submatrix. But Reagan has the token end once, right? There's one end. Inflat is used by Reagan, and it's also used by Nixon. Even though they use different words, right? Inflated, inflation, they end up with one both in this column because it was stemmed. And then Reagan uses free, tear, live, and there are a bunch of zeros, right? Often these matrices are pretty sparse. There are a lot of zeros because a lot of documents just don't include a lot of the words that are used in a given document. And then here you can turn it into a sentiment dictionary, but we will not address that. We will not address that right now. So this is just a basic picture of this text pre-processing. How to go from a sentence, treating it as this kind of bag of words, and creating this document feature matrix, which is just the frequency of these tokens in this document. So that's pretty simple. And this is used very, very widely in political science and the social sciences. Now the point is that these choices matter, right? So you can take 7 potential steps in pre-processing, and that leads to 128 possible combinations of pre-processing steps. You don't have to stem, or you can stem, right? You can remove infrequent words, or you can't. You have a lot of possibilities, and there are 128 in total. The difficulty is that many of these choices are simply made arbitrarily. You can use your best judgment, but often there's no easy theory to guide these kinds of choices. And the point is that the results of your work will frequently be sensitive to these choices. And I'm just going to show you how. And this is just from Denny and Sperling. So this table is just to show that pre-processing varies a lot in practice. So these are 5 well-known articles in political science. And this is the legend for the pre-processing steps that these authors each take with their text. And you can see, as I mentioned earlier, that almost all of these authors lowercase their tokens, right? But not all of them remove infrequent words. So the middle 3 remove infrequent words, but this first set of authors does not remove infrequent words. This last set of authors does not remove infrequent words. So just empirically, researchers actually vary substantially enough in how they pre-process their text. Now I'm just going to show you how this actually matters, how you pre-process your text can actually matter. And what Denny and Sperling do here is they take the policy manifestos from the Labour and Conservative Party in 1983, 87, 92, and 97, and they use a method for estimating the ideology of each of these parties. I'm not going to talk about how they do that right now, but just imagine that they're using this document feature matrix that has been pre-processed in 28 different ways to estimate the ideology of these parties. And we know from expert knowledge that the Labour Party in 1983 should essentially be estimated as the most left-wing of all of these party years. And the Conservative Party in 1983 should be estimated as the most right-wing policy manifesto. And so these white, all these cells in white, so there are 128 rows here, and each represents a separate permutation of the pre-processing steps. And where it is a white cell, it means that based on this pre-processing step, I mean, they don't list them all here, but you can imagine there are all 128 of them, that the Labour Party is in the right rank. Like with this pre-processing step, whatever it was, Labour in 1983, that policy document ended up as being estimated as the most left-wing, and then Labour 87 as the second most left-wing, Labour 92 is the third most left-wing, and so forth, right? And so for these pre-processing steps, everything is kind of in the right order as you would expect given expert knowledge. But these black ones mean that for whatever step for whatever permutation of the pre-processing this is, that Labour in 1983 did not end up being estimated as the most left-wing. And so you see a lot of black here, which is to say that for a lot of pre-processing permutations or possibilities that you could imagine analysts would take, you would end up with these parties out of order, which is to say that the pre-processing actually matters. And this is just with respect to ideology, which we'll have a week about at another time in a few weeks from now. And then this is just the last example of how this pre-processing can affect your results. So this is with respect to topic model, which we're not going to talk about now, but you can imagine that a topic model basically takes text, takes a document feature matrix, and tries to figure out how many different topics are in that corpus of text, that set of texts, and what they are. And so there are ways to estimate the number of topics in a given corpus. And here we have all the 128 different pre-processing, or I guess it's 64 in this case, because they removed trigrams. And you can see that on the y-axis is the optimal estimated number of topics. So when you pre-process the text in these ways, you end up with the topic model estimating a large number of topics. But if you estimate or if you pre-process your text in these ways, you end up with many fewer estimated topics. And this is just to say that pre-processing matters. Whether you make these seemingly arbitrary choices can vastly affect your results. So what do we do about this? So for the moment, I just want you to keep in mind that this is a problem, that pre-processing, just like keywords, thinking about keywords is going to give you different results. Pre-processing decisions can also give you different results. And in later classes, we might look at ways to conduct robustness checks to examine how these choices can actually affect your results. And just to give you an idea of what a robustness check is, you can imagine that you run an analysis with all, let's say, 128 pre-processing steps. Like you pre-process your data with one of the 128 permutations. You get your result, then you do it for the next permutation, you do it for all 128, and you hope that your results are robust or insensitive to how you pre-process your data. And if they are sensitive to it, which is to say that your results, say, differ vastly depending on your pre-processing, then you would want to note that for the reader, and it would give you some pause about how conclusively you can make your decision based on the results.